Okay, so in this video, I will giving you some examples under the topic the coordinate system with the coordinate conversion, and the last one, the vector conversion. So example number one is coordinate, and the rest are for the transformation of a vector. So for number one, so let's first solve number one. So here, given the point 3, 4, -1 plotted at the rectangular coordinate system. Now determine the equivalent of the point in cylindrical coordinate system. So this is just a direct substitution to our formula derived. So this is from this is xyz. This is in rectangular xyz in rectangular coordinate system, and we want to transform that or determine the equivalent in another coordinate in cylindrical coordinate system. So our x is equal to 3, our y is equal to 4, and our z is equal to -1. So from our previous discussion, we derived the formula when we are converting from rectangular to cylindrical. We need to determine, so these are the unknowns, rho, phi, and z. So for rho, our formula for rho is just equal to the square root of x squared plus y squared. And x is 3 and y is 4. So therefore, rho, so this is the square root of 3 squared plus 4 squared. So our rho is equal to 9 plus 16, that's 5, square root of 5. Then next, for our phi, our formula for phi, the derived formula was tangent inverse arctan of y over x. And this should be tangent inverse over y is 4 and our x is 3. So if you take the arctangent of that, phi will be equal to, in degrees, this is 53.13 degrees. Then for z, because we are converting from rectangular to cylindrical, our z is the same, -1. So therefore, our equivalent coordinate in cylindrical will be at 5, 53.13, and -1. So this is now in cylindrical. It's the same point. Remember what we discussed before. We are not changing the position of the point. We are just changing the coordinate system around that point. So it's the same point as 3, 4, -1. So that's number one. Next, for number two. So this is number two. Express the point with spherical coordinates a 2 pi over 4 pi over 6. So this is in spherical coordinate system in both rectangular and cylindrical coordinates. So this is another conversion of point conversion from spherical to rectangular and cylindrical. And letter B, if another point is located at this point, square root of 6 over 2, square root of 2 over 2, 0, determine the distance between A and B. So for letter A, solution. We just need to express point A, which is 2 pi over 4 pi over 6 in rectangular and cylindrical. So first, in rectangular coordinates, so our values for the spherical, we have r should be equal to 2. Then we have theta is equal to pi over 4. And we have phi, that's pi over 6. These are in radian. So be careful with your calculator when the given are in radian. So you need to change your calculator in radian mode, not in the degree mode. And the formula for x, when we are converting from rectangular or from spherical to rectangular, we derive also this one. This is r sine theta times cosine phi. So direct substitution, our x now will be r is 2. Then sine of our theta is pi over 4. then cosine phi, cosine of pi over 6. And solving this using your calculator, it should be equal to the square root of 6 over 2. Then for y, the formula for y is r. So sine theta, still sine theta. Then this time, instead of cosine phi, we use sine phi. Sine phi. Then let's do the substitution again. This will be equal to 2 times sine of pi over 4 multiplied by sine of pi over 6. Then the answer for this, y, will be equal to the square root of 2 over 2. Then what else? We still need z because we're converting to rectangular x, y, z. We need to solve x, y, and z. So our z, the formula for z is just r cosine of theta. Then our r is 2 multiplied by cosine of our theta is pi over 4. Pi over 4. Taking that cosine of pi over 4 and you multiply it with 2 cosine of pi over 4. Then square root of 2 over 2 times 2. So the answer is square root of 2. Our z is equal to the square root of 2. So this is now our coordinate in rectangular. It should be square root of 6 over 2. Then we have y coordinate square root of 2 over 2. And we have the z square root of 2. So this is in rectangular. So we converted or transformed the given, which is in spherical coordinate, into another coordinate system, which is rectangular coordinate. Then for in cylindrical, we also derive this, the formula for converting from spherical to cylindrical coordinates. And using again the given, r equals 2, theta equals pi over 4, and phi equals pi over 6. So in cylindrical, what are we solving? We're solving for rho, solving for phi and z. So for rho, the formula for rho in terms of spherical coordinate system, this is just equal to r sine of theta. And let's do the substitution again. This is 2 times sine of pi over 4. So rho will be equal to the square root of 2. Then for phi, our phi is the same phi as the phi in spherical. They are the same phi. So our phi in spherical is pi over 6. So our phi in cylindrical is also pi over 6. Then lastly, for z, the formula for z is r cosine theta. So this will be 2 times cosine of pi over 4. So z now will be equal to also square root of 2, because again in rectangular you can see that the value for z is also square root of 2. And here we also derive it using our formula, and it's the same outcome. It's square root of 2. Why? Because it's the same point. We are just converting it into another coordinate, and we know that z in cylindrical is the same as z in rectangular coordinate system. So this is letter A. And for letter B, now if another point is located, this point here, square root of 6 over 2, square root of 2 over 2, and 0, determine the distance between A and B. So for letter B, if we have another point which is located at square root of 6 over 2, square root of 2 over 2, and 0. Now, this is in rectangular coordinate system, obviously. So we can use the rectangular version of the point A instead of using the spherical, the given spherical. We already solved the equivalent, this one here, square root of 6 over 2, square root of 2 over 2, then we have square root of 2. So this is point A, and this is point B. Now, if we want to determine the distance between 2 points, just like in analytic geometry, we have we have what we call the distance formula. In two dimension, the distance given 2 points is just equal to x2 minus x1 squared plus y2 minus y1 squared. This is in 2 dimension. In 3 dimensional, you just add z here. So the distance between A and B, DAB, now will be equal to the square root of, so this will be our formula, x2 minus x1 plus y2 minus y1 squared plus z2 minus z1. This is the diagonal of a certain uh, cube or box. And we can let this one our x1, y1, z1, and this is x2, y2, our z2, so that we can solve for the distance between the 2 points. So if our x2 is this one, so this will be 0. Square root of 6 over 2 minus square root of 6 over 2 squared plus y2 minus y1 is also 0. And we have here plus 0 minus the square root of 2. Then you square that. So this will be, you square the square root of 2, that will be just 2. You take the square root again, and therefore the distance between the two is just equal to the square root of 2 units. And obviously that's just the distance, or in the z-axis, the value of z here. So this is how we do conversion of points. Now let's go to the last example. This time we will be converting field and vectors, vector field and vector. The solution. Expressed in rectangular coordinates. So for the first one, letter A, when a field is given, this is a vector field, 1 over r squared AR. So this is just one component. And if you remember our, recall our dot product, because we will be using that, let's just copy our dot product, the one that we derived before here, the table. This one, we'll be using this here. And the other one also, let's just copy it. This one. So these are, for the first one, the first table, this is for the dot product between the rectangular coordinate and the cylindrical, while the second one is for the spherical and rectangular. So in this case, because we want to solve the rectangular coordinates, so we need to transform this into rectangular. So the table that we'll be using is this table, the second one. And in order to do that, we need to use that product. So what are the components of this vector in rectangular coordinates? The same, we have x component in the x direction, we have y component in the y direction, and we have the z component in the z direction. So we need to solve for ex, ey, and ez. For ex, we just do the dot product, because this is just the projection of this vector at the direction of ax. So we take that product of that vector with ax, because we're solving for the component in the x direction. And e is this one, so this is 1 over r squared ar, and you take the dot product, and just do this dot ax. So if you look at our table, what is ar dot ax? Ar dot ax is the sine theta cosine phi. So therefore, our ex now will be equal to sine theta cosine of phi all over r squared. Then next, for the y component, ey, or we can first convert this, because we need to convert also. This is not in the rectangular coordinates. Theta, phi, and r are not in rectangular coordinates. But we know our conversion before. If you remember the formula for x, r sine theta cosine of phi. Y is r sine theta sine of phi. We did it here. This part, r sine theta cosine phi and r sine theta sine phi for y. And for r is just equal to the square root of x squared plus y squared plus z squared. Then we can substitute this here. I can multiply so that this will be, I can multiply r at this part, and I will also multiply r at the bottom. So this will result with, this will become r cubed. So this will be r sine theta cosine phi. Then we have r raised to 3. Why did I do that? Because r sine theta cosine phi is just equal to x. So I just substitute it here. This is just equal to x. Then for the denominator, r is equal to the square root of x squared plus y squared plus z squared. This is r, but our denominator here is cube. So we still need to raise this one to 3. And this will be our e of x in rectangular coordinates. So if you look at this component, it's in terms of x, y, and z. And we repeat the process for EY and EZ. So for EY, we have, again, this one. I just change this with A dot AY, AR dot AY instead of AX. So this is Y. And what is AR dot AY? So in the table, AR dot AY is sine theta sine phi. Again, this is equal to sine theta sine phi all over r squared. And we multiply this again with r. We multiply it with r. So this will be equal to, so our EY now, the numerator will be equal to y. That's r sine theta sine phi. So that's y all over r cube. It's the same as our r cube in EX. So this is just equal to the square root of x squared plus y squared plus z squared. Then you cube this one, raised to 3. And that will be our EY. And lastly for EZ, repeat this again. Let's copy this one. Instead of AY, we use AZ. And what is AR.AZ? AR.AZ is just cosine theta. So here we have cosine of theta all over r squared. And again, we multiply it by r. What is r cosine of theta? So if we go back again, our formula here, r cosine theta is just equal to z. So z is equal to r cosine of theta. So this is just z all over again the cube, the square root of x squared plus y squared raised to 3. So EZ is equal to z all over the square root of x squared plus y squared plus z squared. Then cube. So now we know the components on the different unit vector or directions ax, ay, az. So we can now, or is there a given point? There's a given point at x equals 1, y equals 2, z equals 3. So we need to evaluate also this one in terms of that. But before we do that, we can first collect all the components. For the first one, the x component here. Just copy this one. This is in the ax direction. This is in the ax direction. For ay direction, this is our component. Last, this is in ay direction. And lastly, for az, so this is also plus z in the z direction. So this is now the vector field, but we need to evaluate this at x equals 1, or this is 1, 2, and 3. 1, 2, 3. So this is 1, 2, 3. The vector uh, at 1.123. So x is 1, 2 is y, and 3 is z. So this will be 1 all over the square root of 1 squared plus 2 squared and plus 3 squared. That's 9. Just cube that. And this is in x direction. Plus for y is 2 all over this again. 1 plus 4 plus 9 cube. And the y direction. And lastly, for z, this is 3 all over the square root of 1 plus 4 plus 9 cube in the z direction. So we already evaluated this. So this will be 1, 2, 3, 1 over square root of 1 plus 4 plus 9. That's just equal to 0.019. 0.019 in the x direction. Then we have for the z, 2 over this one, this is 0.038. In the z direction, or in the y direction, this is y. And for the z direction, this is 0.057. So this is now our vector at 0.123. So this is the difference between a vector and a vector field. A vector field is like a function. This is the function. This is the vector field. Well, this one is a vector. It's the value of that vector at that point. So this is for letter A. For letter B now, this is again given another vector here that we need to convert. You can just copy this one here. Letter B. We need to convert this into rectangular coordinates. And there's no given point, so we just need to solve for the field. We don't need to evaluate that. So repeat again the process. What will be our vector in the rectangular? We have EX, EY, and EZ. So we need to solve for those components. EX will be equal to this vector, rho over dot, or squared of rho squared plus z squared. Then you cube this one in the rho direction plus z all over rho squared plus z squared in cube in the z direction. Then we take the dot product because we're solving for EX. We dot it with AX. So if we distribute AX, we have A rho dot AX. So we go back again to the table, A rho dot AX. So that will be equal to cosine of phi. A rho dot AX. That's just equal to cosine of phi. So this will be rho times cosine of phi, because that is A rho dot AX all over the square root of rho squared plus z squared cube. Then for z, az dot ax, we know this one, az dot ax is just equal to 0 because they're perpendicular with each other. So the angle is 90 degrees, so cosine of 90 is just equal to 0. So this is just our ax now, because the second term is just equal to 0. So we don't need to write that. Next, or again, we need to convert this into cylindrical coordinates. So what are our formulas in cylindrical? So if you remember the formulas, cylindrical and rectangular, x is just equal to rho cosine of phi, y is just equal to rho sine of phi, and rho is equal to the square root of x squared plus y squared. What else? That's it, because z is just equal to z. The z in the rectangular is the same z as in the cylindrical coordinate system. So here, the numerator is just equal to x. While the denominator, we have rho squared. Our rho is square root of x squared plus y squared. You square that one, and that will be equal to that, x squared plus y squared. So our ex now will be equal to x all over the square root of rho squared, which is x squared plus y squared, plus z squared then this whole thing will be raised to 3 because this is also raised to 3. That will be our EX. For EY, so our EY will be equal to, so this one instead of AY, it will be aero.ay. What is aero.ay? Aero.ay is sine phi. So instead of cosine phi, it's just sine phi. So this will be rho sine of phi all over the square root of rho squared plus z squared cube. And for the next term, it's az.ay. Again, that's perpendicular. So the answer will be 0. That product will be equal to 0. Then we can substitute again our formula for rho sine phi is just equal to y. And the denominator is the same, the square root of x squared plus y squared plus z squared raised to 3. So this is our EY. For our EZ now will be equal to, so if we make this one AZ, aero.az, what will be aero.az? Aero.az will be equal to 0. So the first term will be equal to 0 here. But az.az is equal to 1 because they are parallel. So the answer will be just this term, z over the square root of that. So this is the z all over the square root of rho squared plus z squared, which is just equal to this, x squared plus y squared plus z squared cube. And this will be our EZ. Then if you look at our answer here, they are the same. Our EY, AX, and EZ are all the same. So we can just copy this one. This will be our field, equivalent field of the given vector field in a rectangular coordinate system. So they are the same field. So this means this one is also, this is the same as in spherical, 1 over r squared AR. They are all the same field. They represent the same field into the different coordinate system. This one is in cylindrical coordinate, this one is in spherical coordinate, and this one is in rectangular coordinate. So this is how we transform our vectors and vector field into one form of the coordinate system into another form of coordinate system.